In this section, we will explore the different data structures available in Panda. This is where things start to get more practical and more exciting. So, let's begin. First of all, you have to keep in mind that there are two main data structures available in Panda. DataFrame, which is two-dimensional, and Series, which is one-dimensional. Let's look into each one of them. A data frame is two-dimensional data structure that may contain one or more rows and columns. Each row is represented by a row labeled called index. Each column is also represented by a column label. Row and column labels can be numbers as well as strings. So that was it for the Panda data frame. And now let's see what a Panda series means. A series is a one-dimensional data structure, i.e. a series contained only in a single row or a single column. Remember that a data frame can also contain a single row or column, but it may have more than one row and or columns as well. The given series consists of a single column. Each row of the column is represented by an index 0 to 9, just as a data frame. At the bottom, we can see the name of the series and the data type of the values in this series. A data frame can be thought of as a collection of one or more series. In fact, each column of a data frame is a series. The series in the previous example was actually a column of the given data frame. We will see later on how can we get a series from a data frame. We can create a data frame using the built-in function pandas.dataframe. We pass a list as an argument to this function and get a data frame. Pandas will automatically add the numerical indices for each row of the data frame. If we do not provide the column labels at the time of creating the data frame, Panda will automatically assign numerical labels to each column as well. Let's see how we can create a data frame using lists. We go to our Jupyter notebook and start by importing Panda. Import pandas. We run this cell. Let's create a two-dimensional list. On the screen in front of you right now is an example of how to input the two-dimensional list. Input what you see on the screen right now, and then let's run this cell as well. Now, let's create a data frame using the list that we created above. Input the data frame as you see on the screen in front of you, and let's see what we get. We run this cell and you can see we have a data frame on the screen. We can see the numerical indices on the left and the column labels at the top. Each row of our two-dimensional list has become a row of the data frame. If we want to have a custom column names, we can provide a list of the column labels to the columns in the panda.dataframe function. Let's see how it works. Okay, so this is the code that we wrote earlier. Let's provide a list of column labels inside the panda.dataframe function to have a custom column labels. Since our two-dimensional list contains two columns, we provide two labels. Yet again, input the cell what you see on the screen in front of you, and let's see what we get. Let's run this cell to see the change. And there you go. Our first column is named fruit and our second column is named color. As stated in the previous section, NumPy arrays are similar to Python lists. We can also create a data frame using NumPy arrays in similar fashion. Let's go to Jupyter Notebook and see how it works. First, we create a list. Once again, input what you see on the screen right now. Now, input what you see on the screen right now to create a new variable. Let's run this cell to see what we get. So here we go. We have created our data frame from a NumPy array. We can also create a data frame using a dictionary. Each key of the dictionary will become a column label. Note that each key should have a list of one or more values associated with it. Again, row labels are assigned automatically by Panda. Let's create a data frame using dictionary. Let's first create a dictionary. Input what you see on the screen right now to make this cell. We run this cell. Let's pass this dictionary to the panda.dataframe function and see the output. Input what you see on the screen. Click Run. And here is our data frame. Column labels are the same as keys in the dictionary. We can also convert a comma separated file into a data frame using the built-in functionality of Panda. There are many resources on the internet where you can download CSV files with millions of rows. Let's jump to Jupyter Notebook to see how to load a CSV file as a data frame. We open our Jupyter Notebook. I have a file in my PC named serials.csv. The pandas.read_csv function takes the path of the file to load it as a data frame. Since my Jupyter Notebook is running in the directory where my CSV file is, I'll only provide the name of the file to this function. On the screen in front of you right now is how I input the function. So we first load our CSV file by providing its name inside the pd.read_csv function and store the data frame in the variable df. We then print df. Let's run this cell to see the output. Click Run and we see a data frame on the screen with 5 columns: name, calories, protein, vitamins, and rating. Also, as you can see, Pandas automatically assign numerical indices to each row. So far, we have only had numerical indices in all of our previous examples. We can also have strings indices using the set_index function. We can make one of the columns of our data frame as the index column. Let's see how it works. In this example, we will be using the data frame that we create in the previous example. Let's print it first. df. Click Run and this is our data frame. Let's make the name column the index. df.set_index brackets name close brackets. Let's run this cell and here you go. The name column is now the index of our data frame. In the previous examples, we changed the index of our data frame. However, let's see what happens if we print our data frame again. Let's print our data frame named df. df. Click Run. We see that our original data frame name df has not changed. This is because most of the functions in Panda do not actually change the original data frame. If we want to change our data frame permanently, we can set in place true inside many of the Pandas functions. Let's change the index of our data frame again, but this time we'll also set in place two true. df.set underscore index brackets name in place equals true close square brackets. Let's run this cell. In the next cell, let's print our data frame, df. Click run. Our original data frame has now been changed and the name column is the new index. The head function gives us the first 5 rows of our data frame or series by default. We can get more rows by passing the required number of rows as an argument to the head function. In the given figure, we can get the first 7 rows of the data frame. To get the rows from the bottom of the data frame or series, we can use the tail function. In the given figure, we get the last 7 rows of the data frame. We can use the describe function to get a statistical summary of the entire data frame. Let's use the describe function to get a statistical summary of our data frame named df. df.describe close brackets. Let's run this cell. We get a data frame that presents the statistical summary of each column of the data frame. We looked at the head and tail functions that give us first n or last n rows. Sometimes we would like to get rows, say from 15 to 20 or 100 to 200. We can use the brackets operator to slice rows of the data frame. Bracket operator takes a start index and end index. Note that the end index is exclusive while the start index is inclusive. Note that the square brackets operator works on row positions and not on their labels. For example, in the given example, the row labels are strings. To slice rows, we pass rows positions to bracket operator and not their labels. Let's slice the rows 1 to 3 of our data frame. Since the end index is exclusive, we set the end index of the slice to 4. Note that the labels of our data frame are strings, but we provide row positions to slice them. df 1 over 4, close brackets. Click run and we can see the output on the screen, rows 1 to 3 of the data frame. Always remember that the bracket operators do not change the original data frame. We can also use the bracket operator to index one or more columns of the data frame. In case of column indexing, we provide column labels to the bracket operator and not their positions. In this example, we will index the first and the last column of our data frame using their labels. Since we are indexing more than one column, we need to provide their labels as lists to bracket operator. Input what you see on the screen right now and then click run. We get a data frame with only the columns we were indexed. Again, no change has been made to our original data frame. If we pass a list of booleans to the brackets operator, we get another data frame containing only the rows for which the corresponding element in the list were true. Let's see how it works. Let's get the third row of our data frame. Now we can obviously slice the rows using brackets operator, but for the sake of this example, we'll pass a list of booleans to the bracket operator. Our data frame contains 5 rows. Our Booleans list also contains 5 elements. Since we just want the third row, we will set the third element of our list to true. The rest of the elements will be false. Input what you see on the screen right now, and then we will run this cell. As you can see, we only get the third row of the data frame. Alright, now on to the next lecture. Sometimes we only want to get the rows of data frame which satisfy a certain condition applied on one or more columns. We can use the bracket operator to achieve this. Let's move on to Jupyter Notebook and see how this works. Let's try to get rows of the data frame in which the values of the calories column are greater than 70. We can directly apply a condition on a column of the data frame. Input what you see on the screen right now, then click Run. And we got only the rows which the value of the calories column is greater than 70. So, what did we do? We first apply a condition on the calories column and got a list of booleans which contains a true for the rows where value of calories is greater than 70, and for false for the rest of the rows. We then passed this list to the bracket operator and got the rows of the data frame for which the corresponding element in the boolean list was true, or the rows which satisfied our given condition. We can also group one or more conditions together using the AND operator. Note that in Panda the symbol for AND is the AND symbol. In this example, we will apply two conditions, one on calories column and the other on protein column. We will use the AND operator to group these conditions. We'll get only those rows of the data frame which satisfies both of these conditions. Open square brackets, df, brackets, df calories, close brackets, over 70, and df brackets protein under 4, close all brackets, and click Run. And you can see that all the rows of the data frame satisfy both of the given conditions, that the value of calories is greater than 70 and the value of proteins is less than 4. Previous example, we had to create a condition variable and pass that variable to the data frame using the bracket operator. In this example, we directly pass our conditions to the data frame using the bracket operator without creating a variable. You can follow any method you want. However, note that if you are using the AND operator, each of your conditions should be inside parent theses. Otherwise, Panda will throw an error. We can also group conditions using the OR operator. We will get the rows of the data frame which satisfies at least one of the given conditions. The symbol in Pandas is the pipe sign. Using the bracket operator, we can slice rows and index columns. What if we want to do the opposite, i.e. slice columns and index rows? Well, we can use LOC and iloc for that. Provide the row labels as the first argument and the column labels as the second argument. The data type of the output will be different based on whether we are indexing or slicing, and whether we pass the argument as list or not. Let's actually see how it works. Let's index the first row and the first column of our data frame named df. I'll pass the row and column labels and not position to the LOC method. The label of our first row is 0 and the label of our first column is name. I should get 100% Bran as output on screen. Input what you see on the screen right now, then click Run. and we do get the desired output. If we pass the labels as lists while indexing, we will get a data frame. We repeat what we did in the previous tutorial, but this time provide the row and column labels as lists. Input what you see on the screen right now, then click Run. We get 100% Bran on screen, but this time as a data frame. We can also use the LOC method to slice rows and columns. We provide a start and end label for rows and start and end label for columns to slice them. Both the start and end labels indices are included. If we slice both the rows and columns, we get a data frame. In this tutorial, we will slice the first 5 rows and the first 3 columns of data frame passing row and column labels to the LOC. We want first the 5 rows and the first 3 columns. We will slice rows from 0 to 4 and columns from name and protein. Input what you see on the screen right now, then run the cell. To see the output, as you can see, the resultant data frame contains first 5 rows and first 3 columns of the data frame DF. We can also use LOC to index rows and slice columns, or slice rows and index columns. In this example, we will index rows and slice columns. The opposite of this is also possible. We index the rows with labels 5 and 8, and slice the first 3 columns of the data frame DF. Let's write our code. Input what you see on the screen. Then click Run. And here you go. We get 2 rows that we indexed and 3 columns that we sliced. How is it going so far? It's time for a small quiz to test your knowledge. Here is the correct answers. iloc works exactly the same way as loc, except that it takes row and column positions as arguments and not their labels. Position of first row is 0, and that of the first column is also 0, regardless of their labels. Let's index the 10th row and the 3rd column of our data frame, named DF, using iloc. Remember that iloc takes positions of rows and columns as arguments and not their labels. The position of 10th row is 9, position of 3rd column is 2. df.iloc brackets 9, 2, close brackets, and hit run. We get the value of 3, which is the 10th value in the 3rd column. If we pass a row and column positions as lists to the loc method, we get a data frame. We can also use iloc to slice rows and columns. Instead of passing row and column labels, we pass their positions to iloc method. Another major difference between iloc and loc is that, unlike loc, the end position of rows and columns while slicing is not included in an iloc. Let's use the iloc method to slice first 5 rows and first 3 columns of our data frame. The position of first 5 rows are from 0 to 4. It's coincidentally the same as their labels, and the positions of first 3 columns are 0 to 2. Since the end positions are not included in iloc, slice rows from 0 to 5 and columns from 0 to 3. df iloc brackets 0 over 5, 0 over 3, close brackets. The resultant data frame contains first 5 rows and first 3 columns of the data frame. Just like loc, we can also index rows and slice columns, simultaneously using iloc. The opposite is also possible. Just remember that iloc takes row and column positions and not their labels. We can add more rows to our data frame using the loc method. It works the same way as adding a key value pair to a dictionary. We provide a new row label to the loc method and assign a list of values to it. Note that the number of elements in this list should be equal to the number of columns in your data frame. Let's add a row with the label 6 to our data frame named df. Our row will contain the values. Input what you see on the screen right now. And let's run our cell. Let's see the output. And as you can see, we do have a row labeled 6 and with the values that we provided. We can also delete rows from our data frame using drop function. Provide the label of the row to be deleted to the drop function and specify axis equals 0 to the permanently deleted row from the data frame, set Inplace equals true. In this example, I'll show you how you can delete a row from a data frame. We will use the data frame that we have been using so far. Input what you see on the screen and follow the instructions. Then let's run this cell. Let's print our data frame in the next cell. Run and you can see the row with the label 2 has been deleted from the data frame. To add a column to a data frame, we use the same notation as adding rows, except that instead of using loc method, we use the brackets operator. This again is the same as adding a key value pair to a dictionary. Let's add a column to our data frame named df. Put what you see on the screen above and let's run this cell. And we have a new column appended to our data frame. We can also use the drop function to drop a column of data frame. To delete a column, provide its label to the drop function and specify axis equals 1. Let's drop the column that we added in the previous example since it does not make any sense. Input what you see on the screen above and click run. And as you can see, the last column has been dropped. To sort the values of a data frame with respect to a column, we can use the sort_values function by default. This function sorts values in ascending order. One good thing about the sort value function is that if the column values are numbers, they are sorted numerically. If the values are words, they are sorted alphabetically. In this example, we will sort the values of our data frame with respect to calories column in ascending order. Input what you see on the screen right now, and let's run our cell. Our data frame has been sorted with respect to the calories column in ascending order. To sort a data frame in descending order, set ascending equals false in the sort_values function. So, to sort a data frame in descending order, we will set ascending equals false in the sort_values function. Input what you see on the screen, then run this cell to see the output. And here you go. We can see the data frame has been sorted in descending manner with respect to the calories column. So to save a data frame as a CSV file, we use the to_CSV function, which takes a file name to store the data frame. If a file with a given file name already exists, it will be overwritten. Otherwise, a new file with the provided file name will be created. If you do not want to store the index column in the CSV file, you can set the index_label equals false in the to_CSV function. Let's write our code. In this example, we will look how can we convert a data frame into a CSV file. We will use the to_CSV function for this. I'll provide a file name that does not already exist in the given directory. Input what you see on the screen, then click Run. As you see, we get the same data frame that we have stored in the CSV file. Pandas also assign numerical row labels to each of the rows. We can also concatenate two or more data frames using panda.concat function. The data frame will be concatenated one below the other. We can also join data frames side by side by specifying axis equals 1 in the pandas.concat function. Let's move on to Jupyter Notebook to see how this works. I have two data frames named df and df2. So here are two data frames which have same row labels. Let's concatenate both of these side by side. Put what you see on the screen, then click Run. And you can see that the two data frames have been joined together. Sometimes we want to have our data frame divided in groups and then apply some aggregate functions on each column. Consider the data frame given in the figure. It has 4 rows and 2 columns. The column gender has 2 unique values, male and female. Split our data frame into parts. First part contains the rows where gender is female and the second part contains rows the gender is male. If we wanted to find the average score of each of the gender, the resultant data frame would have looked like the one in the figure. Concatenate the two data frames together and we get the data frame in the picture. In summary, we split our data frames into 2 parts based on the unique values of one of the columns, i.e. gender. We applied the mean function, which is aggregate function, on the remaining columns of the data frame. We then finally join the 2 splits together. The groupby function works exactly the same way, making our lives easier. Let's see how we can use the groupby function to achieve what we discussed. I have a data frame named df. Let's print it. df. Click Run. The data frame looks the same as we saw in the slides. Let's group this data frame based on gender column and apply the mean function, all of the columns of the data frame. Remember that aggregate function is not applied on the column used to group the data frame, which is this case in the gender column. Input what you see on the screen right now, then click Run. And here we go. We see the desired output on the screen. As stated earlier, the aggregate function is not applied on the columns used to the group data frame. Here is a list of common aggregate functions mean for the average sum for sum of all values. Max and min give the maximum and minimum values of all column respectively. Median gives the median. Count gives the total number of values in the column, and std used for the computing the standard deviation of a column. We hope you have enjoyed learning this module as much as we enjoyed teaching it. Here are some resources for you that you can take the help from. Remember, never stop learning.